Hello! In this video, we are going to prove the following theorem. The square root of 2 exists. Well, more precisely, we're going to prove there is a unique positive real number r such that r squared is equal to 2. Now, in proving this theorem, we have three preliminary results we're going to use. The first one is given any two positive real numbers, a and b, if a squared is less than b squared, then a is less than b. Here's the second preliminary result. Given any two positive real numbers, a and b, if a squared is equal to b squared, then a is equal to b. And here's our third preliminary result. Given any positive real number x, there exists a positive integer n such that 1 over n is less than x. Now first, we're going to show that there exists a positive real number r such that r squared is equal to 2. And then we're going to show that it's unique. So let's start with existence. And to start out, let's consider the following set. We consider the set S, which we say is the set of all real numbers x, such that x is greater than 0 and x squared is less than 2. Now what we're going to do is we're going to show that S has a least upper bound, because we expect the least upper bound of S to be positive, and we expect the square of the least upper bound to equal 2. And to show that S has a least upper bound, well, if we recall, every non-empty subset of real numbers with an upper bound has a least upper bound. So we're going to start out by showing that S is non-empty. Well, of course, 1 is an element of S, so S is non-empty. And to see that S has an upper bound, we can show, for instance, that 3 is an upper bound of S. To see how, well, we're going to show that every element of S is less than or equal to 3. So give me an arbitrary element of S. I'll call it x. From here, we want to show that x is less than or equal to 3. Well, since x is an element of S, this tells us that x is greater than 0 and x squared is less than 2. And we know that 2 is less than 9, and 9 is equal to 3 squared. And now we can apply lemma 1. If we take a and b to be x and 3 respectively, well, yeah, x and 3 are both positive, and also we know that x squared is less than 3 squared. So it follows that x must be less than 3. And since x is less than 3, we have that x is less than or equal to 3. Now putting this together, we see that under the assumption x is an element of S, it follows that x is less than or equal to 3. Since x is arbitrary, this means that every element of S is less than or equal to 3. And that's precisely what it means for 3 to be an upper bound of S. So now that we know S is a non-empty subset of real numbers with an upper bound, this tells us that S must have a least upper bound. Another name for a least upper bound is a supremum. So really, it follows that S has a supremum. And I'll call the supremum of S R. And our claim is that R is a positive real number that satisfies this condition. And to see how, well, it turns out it's going to be useful to know that R is greater than 1. The reason why R is greater than 1 is because, well, we know that 5/4 is an element of S, right? Because 5/4 is greater than 0, and you can easily show that 5/4 squared is less than 2. And because R is the least upper bound of S, of course, R is an upper bound of S. So every element of S is less than or equal to R. So in particular, 5/4 is less than or equal to R. We know that 5/4 is greater than 1. So this tells us that R must be greater than 1. Right, so it's going to be useful to know this. So since R is greater than 1, yeah, R is positive, so all that's left to show is that R squared is equal to 2. Now, there are three possibilities. Either r squared is equal to 2, r squared is less than 2, or r squared is greater than 2. What we're going to do is we're going to eliminate the possibilities that r squared is less than 2 and r squared is greater than 2. So that we're left with only one possibility, and that is r squared is equal to 2. So let's first eliminate the possibility that r squared is less than 2. So, assume for a contradiction, r squared is less than 2. Then, 2 minus r squared is greater than 0. Now, since r is positive, of course 2r plus 1 is positive. So because 2 minus r squared is positive, it follows that 2 minus r squared over 2r plus 1 is positive. And now, let's apply lemma 3 to this guy, right? Taking x to be this guy, well, yeah, this guy is positive, so we're a positive real number. So there is some positive integer n such that 1 over n is less than this guy. And now, multiplying 2r plus 1 on both sides, we get that 2r plus 1 over n is less than 2 minus r squared. Now, since we're working under the assumption that r squared is less than 2, well, based on the way that the real numbers work, we should intuitively expect there to be some real number slightly bigger than r, whose square is also less than 2. In particular, we're going to show that r plus 1 over n squared is less than 2. Now, if we expand this out, we're going to get r squared plus 2r over n plus 1 over n squared. Now, we can agree that 1 over n squared is less than or equal to 1 over n. And because 1 over n squared is less than or equal to 1 over n, we have that this must be less than or equal to this, where all we did was we replaced 1 over n squared with 1 over n. And then we can combine these two guys into a single fraction. So we have 2r plus 1 over n. But we know that 2r plus 1 over n is less than 2 minus r squared. And because of this, it follows that this must be less than this, where all we did was we replaced 2r plus 1 over n with 2 minus r squared. And we know that this is equal to 2. So putting this together, we see that r plus 1 over n squared is less than 2. So we have all the information we need to show that r plus 1 over n is an element of S. Right? To see how that's the case, well, if we take x to be r plus 1 over n, well, yeah, we know that r plus 1 over n is greater than 0. The reason why is because, well, we know that r is greater than 0 and 1 over n is greater than 0. We also just showed that r plus 1 over n squared is less than 2, right here. So yeah, r plus 1 over n is an element of S. But then, since r is an upper bound of S, this means that every element of S is less than or equal to r. So in particular, we must have that r plus 1 over n is less than or equal to r. But wait a minute, this is absurd, because we know that r plus 1 over n is greater than r. So we reached a contradiction. Our assumption that r squared is less than 2 led us to a contradiction, so we have eliminated the possibility that r squared is less than 2. Now we're going to eliminate the possibility that r squared is greater than 2. Now we're going to have to move back to the top since we ran out of room, so let me just write some things down for safekeeping. Okay, so now let's assume for a contradiction that r squared is greater than 2. Well then, in this case, r squared minus 2 is greater than 0. And again, 2r plus 1 is greater than 0. So because r squared minus 2 is greater than 0, we have that r squared minus 2 over 2r plus 1 is greater than 0. And then let's apply lemma 3 to this guy, right? We have that there's some positive integer I'll call m, such that 1 over m is less than this guy. And now, let's multiply 2r plus 1 on both sides of the inequality. If we do that, we get 2r plus 1 over m is less than r squared minus 2. Now, in this case, it turns out it's going to be useful to consider the negation of these two. That is, if we multiply negative 1 on both sides, we get that the negative of this is greater than 2 minus r squared. Now, we're working under the assumption that r squared is greater than 2. And based on how the real numbers work, we intuitively expect there to be some real number slightly less than r, whose square is also greater than 2. Well, our claim is that r minus 1 over n squared is greater than 2. Now, if we expand this out, we get r squared minus 2r over m plus 1 over m squared. Now, since 1 over m squared is positive, and the negative of 1 over m is negative, of course, 1 over m squared is greater than the negative of 1 over m. And because this is true, it follows that this must be greater than this, where all we did was we replaced the 1 over m squared with the negative of 1 over m. Next, let's take these two terms and factor out the minus. Now, adding these two fractions together, we get 2r plus 1 over m. But we know that the negative of 2r plus 1 over m is greater than 2 minus r squared. And because this is true, this must be greater than this, where all we did was we replaced the negative of 2r plus 1 over m with 2 minus r squared. And we know that this is equal to 2. So what we've shown here is that r minus 1 over m squared is greater than 2. It turns out that r minus 1 over m is also positive. To see how? Well, since r is greater than 1, and 1 is greater than or equal to 1 over m, this tells us that r must be greater than 1 over m. So r minus 1 over m is greater than 0. Now, what can we do with this information? Well, we can show that r minus 1 over m is an upper bound of S. In other words, we can show that every element of S is less than or equal to r minus 1 over m. And to see how, give me an arbitrary element of S. I'll call it x. Well then, this means that x is greater than 0 and x squared is less than 2. But we know that 2 is less than r minus 1 over m squared, so x squared is less than r minus 1 over m squared. So we can apply lemma 1. If we take a and b to be x and r minus 1 over m respectively, well yeah, they're both positive, and we know that x squared is less than r minus 1 over m squared. So by lemma 1, it follows that x is less than r minus 1 over m. And since x is less than r minus 1 over m, we have that x is less than or equal to r minus 1 over m. Putting this together, we see that under the assumption x is an element of S, it follows that x is less than or equal to r minus 1 over m. Since x was arbitrary, this means for all x in S, x is less than or equal to r minus 1 over m. And that's precisely what it means for r minus 1 over m to be an upper bound of S. However, since r is the least upper bound of S, this means r is less than or equal to every upper bound of S. So in particular, r must be less than or equal to r minus 1 over m. But this is absurd, because we know that r is greater than r minus 1 over m. Our assumption that r squared is greater than 2 leads to a contradiction, so we have eliminated the possibility that r squared is greater than 2. So we're left with only one possibility, and it's that r squared is equal to 2. So at this point, we have proven existence, right? We have shown that there exists a positive real number that satisfies this condition. So now, we want to prove uniqueness, right? We want to show that this is the only positive real number that satisfies this condition. And to prove uniqueness, suppose we have 2 positive real numbers that satisfy this condition. I'll call them R1 and R2. The whole goal is to show that R1 is equal to R2. Well, since R1 squared and R2 squared are equal to the same thing, they must be equal to each other. But then we can apply lemma 2. If we take A and B to be R1 and R2, well, yeah, R1 and R2 are both positive, but also R1 squared is equal to R2 squared. So we can conclude that R1 is equal to R2. And this was the whole goal of uniqueness. So putting this together, we see that given any 2 positive real numbers that satisfy this condition, well, they must be equal. So there can only be 1 positive real number that satisfies this condition. So because we have proven existence and uniqueness, we have shown that there is a unique positive real number that satisfies this condition. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.